All right, welcome everyone to our second day of mini course by Mark Iwan. It's a pleasure to have him speak for the second part of this course. The structure of the day will be the same as yesterday, so 1 hour lecture, then 15 minutes break, another hour lecture, 15 minutes Q&A, and that will be it. So take it away, Mark. Thank you.
Great. So welcome to day 2 to the survivors. Last time, if you remember, we were pretty much occupying the computer science universe of compressive sensing and talked about these sublinear time methods. If you have these K alpha incoherent matrix constructions that you then take this Cauchy-Rao product with bit testing matrix, for example. And then the claim is that lets you do sublinear time compressive sensing with best term approximation guarantees. Probably you're wondering how this could ever have anything to do with function approximation. So that is the bridge that I hope to cross today and show you at least one nice way of getting function approximation out of these methods. So the first ingredient to be able to do that is going to be to have another bit testing matrix that's Fourier friendly. So I'll call this example 2 of a bit testing matrix. This is going to be prime based construction. And the claim that I'll try to make more clear going forward is that this is going to be a Fourier-friendly type of construction that lets us do things nicely with respect to the Fourier basis later in a particular way. Okay, so let's see. Right now, though, we just want one of these bit testing type matrices. So K alpha coherent type of matrix construction here. So let me choose any integer that I want. That's my cartoon N for integer. And so given that, we're going to have our testing matrix P sub n that we're going to create. It's going to be built using some co-prime numbers. So again, to remind you, these are always 0, 1 matrices. I'll say it has m prime rows and n columns. And we are gonna build it using some co-prime numbers. So we're gonna build this guy built using m tilde co-prime numbers, which could just be primes if you like. They're the easiest co-prime numbers to guarantee. So P1 through PM tilde. Okay, and I just want to make sure that these numbers have a product that's bigger than n. So I'll maybe say n tilde is their product. And I just want to make sure that that's at least as big as n. And that's all we sort of need here. So, okay, given these ingredients, I'm going to define the matrix this way then. So first of all, I'll tell you what the size of the rows are. So what this m prime is. So it's going to turn out to be the sum of the primes that I'm using here, plus 1. Right? So we have the sum of primes. This tells you why we're going to have, for large n, at least a small number of rows, because we have product of primes being about n here. And we just have sum of primes being our number of rows. Right, so when n is large, you can expect this is going to have a small number of rows. And this will just be the first n columns of the following matrix. So what am I going to do here? I'm just going to sort of define a matrix blockwise, so to speak. So as before, I'm going to have a row of 1s for the first row. So I'll have a row of 1s here for the first row. Just repeat that forever. this way. And then for every one of my primes, I'm going to repeat a bunch of identity matrices of the size of the prime until I run out of columns. So this, for example, is a P2 by P2 identity matrix. Okay. All 0, 1 matrices, and I can sort of define things this way. So as an example, see what this sort of stuff looks like. P6, if I use P1 equal to 2 and P2 equal to 3, so first two primes, that's going to be this matrix. It's going to have a row of 1s. Then it's going to have 3 2 by 2 identities. I can sort of write them down blockwise this way. And then it's going to have 2 3 by 3 identity matrices. So, right. So here's an explicit example of what one of these guys looks like. Okay, so this is going to turn out to be a 6 by 6 matrix. And it's going to be one of these bit testing matrices where 6 is just a little bit too small for it to make sense, but you see as it gets a little bit bigger, it'll start making sense. So this has a lot of structure.
But what do you do if the product of J's is strictly bigger than n? And you can't fit like these blocks like perfectly.
You just lay them out until you get bigger than n, and then you quit. You can think of it doing that way. Or we can give a column-wise description of what that
But
would
it
be.
still has to have n columns.
Yeah, yep. So I mean, I can repeat the 2 by 2 matrices until the next one gets bigger than n, and then I'll just fill out a portion of that matrix.
Oh, you don't
Yeah,
fill
just
the whole-
truncate the
Okay.
full thing. Yeah.
That's not clear from that.
Yeah. So yeah, you repeat these forever, for example, and then you take the first n columns of this sort of infinite repeating guy, is if you want to think of it that way. Or equivalently, I guess. Right, we sort of need a way of generating the nth row quickly. So there's an easy way of doing it row by row. So the nth column of this guy. So I guess I can denote this way maybe. It's a little bit terrible notation, but so what is this going to be? So I know what my primes are, my P1 through Pm tilde. I always put a 1 first, and then I just take the canonical basis vector of size P1 for the first prime, and I will pick the one that is n mod P1. Right? So this is going to be a vector of size P1. So that's my first prime. Then I will take the next one, which is n mod P2, and it will be, I'll make it of length P2. And I'll just go ahead and continue that until I get to my last prime. So as long as I know what my primes are, I can just generate these standard basis vectors and stack them on top of each other, and that's going to be the row of the nth row of my basis vector, or the nth row of my bit testing matrix, I should say. All right. Good. Any other questions? Hopefully that makes some sense. So this operation effectively defines the map that we talked about before that you generally want to be fast. Right, so from this, I can generate the nth column quite quickly. I just need to take some mods and stack out some zeros and ones, so that's easy. So we can also invert this function quickly, which remember is something that we want to do if we manage to do some bit testing in order to determine a column that encodes a heavy element, something we were doing before. We need to be able to figure out which column it was in order to identify our support, our associated support basis. So we can do this as well. So given the nth column of this guy, what are we going to do? It's going to look like this, right? So what we can automatically do is, knowing this structure, we can read off what the column is, mod P1 through Pn tilde. So the first step is going to be to read off n mod P1, n mod P2, etc. from the basis vector, right? We have all of those guys. And now comes the reason why you might want to remember what the Chinese remainder theorem is. We then go ahead and solve for n using back propagation and the Chinese remainder theorem. But really, it's just using back substitution, I should say. Right. So, and what I mean by that is, if n is congruent to, what do I have here? X mod P1, then we know that n has to be equal to x plus some other number times P1, right? And now we also know that f is congruent to, that if n is congruent to z mod P2, we can substitute this in here. Then x plus y P1 is congruent to z mod P2. P1 is relatively prime with P2, so it has a multiplicative inverse mod P2. So I can now solve for y, and then I figure out what this thing is up to a multiple of P1 times P2, and then I continue. And I know n is less than n. Little n is less than this, and their product is bigger than this. So when I have finished the process, I know what n is, right? Okay, so just doing this again fast. You can do this on the order of the number of primes that you have in order to figure out what your column number was and invert this function. Okay, so the bit testing sort of structure here should hopefully look kind of familiar compared to this easier bit testing matrix that didn't have primes floating around. If not, please ask. And then you can generalize to the noisy setting where you don't have an exact. So let me just say this. So same as for bit testing. We're going to have the nice sort of situation where if I have an exactly one sparse vector that looks like this, right? I can solve things exactly the same way. So this is going to be equal to gamma times the jth column of this guy. And now that means that I can easily go ahead and use my fast inverse to figure out what both gamma and j should be. So we can solve this the same type of way we did before. Any non-zero entry is going to be your gamma, and then you normalize things so it's 1 and stuff it into this inverse process, and you have your j, and you know everything. Okay. And if instead you have the type of situation where you have noise added on, but relatively low norm noise, then you can do a bit testing type situation here, except now instead of figuring out which bit you've encoded as you go down and do bit testing against this matrix. We are instead going to find, what J is mod each of these primes and then do reconstruction this way. And we'll just do it by comparison. So for each prime, P, right, or P sub L, whichever prime you happen to be caring about at the moment, you're just going to find the maximum possible residue of the sum of all the elements that are in J, whose indices are congruent to K mod PL. And if you look at the structure of this matrix, you notice that that's exactly the information you have here. So here you're going to have the sum of all of the even elements starting at the 0th column. In this row, this will give you the sum of all the odd elements of the vector X. This will give you the sum of all the elements congruent to 0 mod 3, right, this row. So you have all of that information encoded in here. So you can figure out all of the residues by looking for the maximum size of this guy. And as long as this dominates the noise, you'll end up finding the correct residue for each of the primes, and then you reconstruct. It's going to be exactly this thing. So there's going to be an associated row of Pn that you're taking as an inner product with X, and you're going to have all of those measurements. Okay. And that'll give you a good choice for the residue of this important column mod that prime. Okay. All right, excellent. Any questions about this sort of construction? This is maybe a little bit different than the bit testing one, but all the same sort of ingredients, slightly different way. Okay, so that's going to be the bit testing matrix we want to use in the Fourier setting, I claim. We'll talk about why in a little while. We also are going to need these K alpha coherent matrices to work out for us. But this type of construction, I claim, can give you K alpha coherent matrices quite easily as well. So the same type of thing, I'm going to use primes, and I'm going to build exactly this type of matrix, and I'm just going to leave the ones off the top. And otherwise, just fill out these identity matrices in the exact same way. So, right, same type of thing. I'm going to want some different choices of relatively prime numbers, possibly. So I'll call them Qs. And I'm going to take capital K of them because I want a K alpha coherent matrix. And you can see from this definition of the rows that if I leave this one off the top, I'm going to have exactly K1s in each column, given this definition, right? So I'll use K of these guys. All right, so I'm going to do this. And I'm going to let alpha be some number smaller than K. That's such that the first few primes, one through alpha, are just barely smaller than n. If I want to be economical about my choice, at least. So I want alpha plus one of these guys to be greater than or equal to whatever n is. And n can be just a little bit bigger, possibly, than the product of the first alpha primes. So given this, then same type of matrix, just using a little more primes and not putting the ones on top. I'll take Qn and define it in the same sort of way over there. It's going to be a number of rows that's equal to the sum of these primes. By n. right? So the sum of the number of primes I use, and it's going to be the matrix with nth column defined as over there. Just for the sake of writing it down, I'm going to take n mod q1, where this is the canonical basis vector of length q1, and then I'll repeat that down to the kth prime. Right? And that's why I end up with the sum of the number of primes as my number of rows. Okay, again, fast for the same reasons as before. And then the claim is that Qn is going to be K alpha coherent if we build it this way. All right, so that's my claim. And this one is not too difficult to prove, so let's sort of see why it's true. So first, I guess by the definition up here, it's pretty clear to see that there are going to be exactly K1s in every column. So the K part is taken care of. So every column has K1s by construction. I would add the word clearly, but I'm usually annoyed when people write that in proof, so I won't. I'll just say, if you look at it long enough, it will become clear that it's true. Well, it may not be clear immediately. Okay, so the
Proof by staring.
yeah. All right, so these are all, they just have 1, 1 in them, right? And there are K of them, and we're stacking them, so there are K1s in each column. That's the proof, effectively. I ran out of chalkboard. So that's it. So the next thing we want to do is figure out what the inner product bound is for these guys. And only because I said that knowing the Chinese remainder theorem would be helpful, I will do this part just so that I'm not so obviously a liar. Okay, so to see the alpha bound is going to hold for us, we can take two different columns. I'll take the kth column and I'll take the nth column and I'll take their inner product using the notation from last time. So let's think about what this is going to be. This is going to be the cardinality of the set of primes that we used in creating this guy. That have the property that, so when are these are 0, 1s, they're only going to add something to the inner product when two entries in these columns overlap with one another. And they're only going to overlap with one another when K and L are congruent to one another mod the associated prime. So it's going to be, right, such that K is congruent to L mod Q. Oops. And I think, yeah, that's fine. I thought I had a nesting problem for a second, but it's fine. Okay, and so it's going to be the cardinality of this set, and the Chinese remainder theorem, or at least one way of writing it, tells you that this can't happen very much. And that's basically it. So here's my application of the Chinese remainder theorem. So effectively an equivalent variant of it to what you might see in other places. If I choose two values that are between n-1 and 0, and I have some numbers which are going to be primes, that are relatively prime one another. So they don't necessarily have to be prime, but if they're primes, it's easy to check that they're relatively prime. To the left, right? Then the following implication holds effectively. So n mod x1, if I take this, I'll create a vector of length alpha by taking n mod each one of these values. And it happens to be equal to the other guy, m mod each one of these values. Then one of two things has to be the same, has to be true. Either m has to be equal to n, which is something we've eliminated by assumption up here because k and l are not the same by assumption, or the product of these relatively prime values for which this happens has to be strictly less than n. Okay. So if these are equal, then all of these mods are going to be the same. So the sets value is going to be satisfying this equality. But I said k and l aren't the same, so it means that the product of these guys has to be less than n. And how many times can that happen? Well, I picked my alpha so that that's the most that it could possibly happen, right? So an application of this, of Chinese remainder theorem, implies that this value has to be bounded by alpha. All right, good. Excellent. Yes. So what time is it? 2:30. Good. Okay. So if you want to know how many rows you can get away with in this construction, which is a very sort of good type of question to ask, we can talk about that. So if we go ahead and take Q1 through Qk to be the first capital K prime numbers, first K primes, then it's going to imply that their sum, which is going to be the number of rows here of this matrix, is going to be bounded by k squared log k. So their sum is going to be bounded by k squared log k. And it's actually not too difficult to see that this is going to be true. You can even improve this estimate a little bit. It's a little rough. The prime number theorem tells you that the kth prime is bounded by k log k. So a nice sort of analytic number theory result. And so you have k of k things that are all bounded by k log k. K squared log k. All right, that's it. So you just have to look up a little bit of number theory stuff. Excellent. Good. And for that matter, alpha can also be made quite small. So if you take a look at what alpha is, if you use these similar primes, right? The first prime is 2, bigger, has to be bigger than 1. And so there are going to be at most log base 2n primes that you have to use. In fact, you're going to have to use a bit less than that because the primes grow in order to have this inequality hold. So alpha can be chosen to be log n size, right? So by that argument. And in fact, you can make that a little bit better as well. If you want to play with your log factors, you can improve that. So alpha is going to be log n in size, just by comparing the two. All right. Good. So end result here, there's this prime-based way of creating both bit testing matrices and k-alpha coherent matrices that are going to let all of this sublinear time approximate compressive sensing stuff work that we talked about yesterday. That's the main message you have to believe at this point. Any questions about this before I possibly begin to explain why this has anything to do with a sparse Fourier transform?
Sorry, Mark, can you repeat again why is it important to have alpha of log n size?
Oh yeah. So if you remember these, the recovery theorems that we had for k-alpha coherent matrices,
Yeah.
we wanted k to be something like 4 alpha s plus 1, I think. Right. That was. So this says that I can make k be like s log n size, and then the total number of rows is going to be something like s log squared n. You know.
Okay.
Right, for this deterministic construction. So you get s squared times some log factors, and then you can improve the log factors if you want to use some more complicated number theory stuff. But yeah. So that's why we care if we want to go back and use the stuff from last time.
Thank you.
Very good. Any other questions? Okay, let me see. If not, perhaps I will move this over here. And remind us what our total measurements look like in order to use these median recovery and support identification methods. So we have this row-wise Cattry-Rao product business going on. And the point is that if we take a Cattry-Rao product of a bit testing version of this prime-based matrix and a k-alpha coherent version of the constructed by these prime-based guys, we're going to end up with another matrix that has a bunch of zeros and sort of ones in every place that's congruent to something mod their product. Right, so it's going to maintain this sort of number theoretic structure that we have. So let's just write that down, because it's going to be important in a second. Okay, so this is my Fourier friendly sort of overall sublinear time algorithm matrix. And it's going to be this row-wise Cattry-Rao type product of Qn with Pn, the way I've just defined them. It's going to be a 0-1 matrix. And this is what we'll actually use in our sublinear time algorithm. What we need to supply our sublinear time compressive sensing methods. Okay, and if we construct it the way we were just talking about here, so we take the first few primes for each one of these guys, you can see that you can get away with a number of rows. It's going to be like k squared times log factors. You can make it, you can bound it sort of roughly by log cubed n. Rows are going to be in this thing. So again, sort of roughly what you would want for a deterministic compressive sensing type of guarantee, or at least what you would expect you could get. And more importantly, for what we'll talk about when we sort of jump to the Fourier basis considerations here. To write down what I said verbally a little while ago. So every row of this matrix, which is a product of these two direct combs, effectively, is going to look like the following. So it's going to be every entry of this guy is going to have the following type of structure. So let me see if you'll let me get away with this notation. So it's going to have ones in position K if, so there's going to be some J associated with this Jth row, right? And there's going to be some residue mod J, mod that prime associated with this row. So here it's going to be something mod a product of two primes is going to be sort of what this row is associated with. And there'll be a 1 in every entry that's congruent to that. So just to make sure that that seems reasonable to you at least. So it's going to have 1 if K, this column number, is congruent to some residue, which I'll call Hj associated with that row, mod some number Xj. And if you think about it, this number Xj is going to be a product of two of our primes, one of our P primes and one of our Q primes that we sort of use to create this and this matrix. So that's the sort of structure we're going to have here. So every row will have this structure, and if you believe that, then we can sort of go forward and see why it's going to interact nicely with the Fourier basis. All right. So let's see why we can do a sparse Fourier transform using this thing. So effectively, why is this Fourier friendly? Okay. So let's get some function that we're interested in. So I'll go ahead and look at a trigonometric polynomial, f. So I'll say this is indexed by frequencies from -n/2 to n/2. And if n is even, you can decide which one to leave off or whatever side, doesn't really matter, right? And I'll say its kth Fourier coefficient is f hat k, and it's being multiplied by e to the I kx. So this is my trigonometric polynomial. And we are going to assume that our Fourier coefficients, sort of, I list them in a vector of length n, well, of length n plus 1, I guess. It doesn't really matter how you order it, but let's say from -n/2 to n/2. We're going to assume that this thing is k-sparse or approximately k-sparse. Or, sorry, s-sparse. I don't want to change what I'm using for my sparsity. So we have a function whose Fourier coefficients are approximately s-sparse, right? That's what we're interested in approximating here. And so just a little bit about this sort of setting. In this type of setting, there is nothing stopping me from oversampling my trigonometric polynomial, so taking more equally spaced samples than I need to. So let's give ourselves that freedom. I know we want to think about using a small number of samples, but we will eventually. Right, so we have the freedom to choose any integer we want bigger than n plus 1. Go ahead and be crazy, make it, a quadrillion if you want. And then we can let f of this huge size be equal n tilde equally spaced samples from the interval 0 to 2 pi, right? So I'm just going to take equally spaced samples. And stick them into this entry, or sorry, as entries into this vector. So the nth entry will be my function f sampled at a multiple of 2 pi over n tilde. And I can certainly do this for all L equal to 0 to n tilde. Yeah, n tilde. Okay, great. And then in that case, these samples are going to be equal to an n tilde by n tilde DFT matrix that's going to have entries of e to the 2 pi I k whatever L over n, right? So without the negative sign, I'll go ahead and define it that way, times my little sparse vector packed here, and then I can put a bunch of zeros, as many zeros as I need to make the dimensions balance, right? And the point is, this thing is still approximately sparse. Clearly, because I just stuffed a bunch of zeros in there. A bunch of zeros at the end. And these are my equally spaced samples from this guy. So that's great. All right, wonderful. So from what we did this last class, if we can compute MF times the Fourier coefficients of the smaller vector, then we have a sublinear time algorithm for approximating, for learning what this is, right? I just take that, I stuff it into the support identification and medianing algorithm that we sort of described, and I get an approximation back for the Fourier coefficients that's accurate and runs in sublinear time. So this is what I want to compute, and then I claim we're algorithmically finished. So we just have to figure out how to do this. The problem is we don't have access to the Fourier coefficients. Instead, we want to just look at a small number of samples of f. So we only get to see, let's say, these samples, potentially oversampled version of f. And we don't want to look at too many of them either, because that would totally defeat the purpose of having a fast algorithm for computing the FFT, right? So what can we do? All right, so we're just going to do the following. So we want to learn or compute this guy, and then we're done algorithmically. If you believe the stuff we talked about yesterday, at least. That's going to be equivalent to learning. So I can take all of the rows of this guy, which have this periodic structure, and extend them forever if I want, or at least until I have n tilde columns, right? So let me extend this thing. And then sample, right, my extended Fourier coefficients with the zeros packed there, and sort of point out this is going to be MF in the beginning, and then we're going to have a blockwise bunch extension where I stuff a bunch of extra zeros and ones in to fit the pattern, right? So I can do that. This only hits zeros, so I'm still learning the exact same thing. Then the point is, to make a long story short, this extended guy, I can go ahead and multiply the inverse of my DFT matrix times the DFT matrix times the Fourier coefficients. So I'm just going to put an inverse of this guy in here and itself. So I've done nothing. Okay. Right. Yep, that works. And so what is this? These are the samples that I have access to. Right. So this is going to be exactly, I'm just using this sort of formula here. Right. So this is going to be, the point is, what I want to learn is actually the same as this times the samples that I claim to have access to on my sampling grid. So I'm just doing a substitution for this n part, right? All right. So what is the trick that's going to let this work? Well, aliasing is going to save us. It's usually something, I like it because aliasing is usually something that plagues you in numerics. And here I'm going to use it to save us, right? So take that numerical phenomena. Anyways, so the point is, this guy looks like a bunch of rows that have Dirac type structure. These are like Dirac comb, little discrete Dirac combs, and I'm multiplying it against a discrete Fourier transform matrix. And so the result is going to be ridiculously sparse, another ridiculously sparse Dirac comb. Okay, so you can believe that, and you can sort of calculate what it looks like. You're going to end up reweighting things appropriately. And so this is going to actually turn into the following. I'll spare you the calculation, or we can do it if you want. But the stuff in the blue box, if you try it out, is going to end up looking like the following. So what we're going to get is an x1 by x1 discrete Fourier transform matrix being multiplied against a subsampled portion of this vector. And the subsampled portion, that's assuming that I pick n tilde to be such that all the xi's divide it, and I can make it anything I want. So I'm going to make it a multiple of all these values that I have. Where was it? I'm going to make it a multiple of all these values that are associated with this matrix, right? So all of these guys are going to divide n tilde, and I'll just choose n tilde big enough so that works. Right, so that's not an issue. So with that particular choice of n tilde being the product of all those things, I'm going to get, I guess I did want that I have a little Fourier transform of size x1, where x1 is that first product of the two primes. And the vector that I have to multiply it against is going to be a subsampling of the very dense set of equally spaced vectors that I had before, and they're going to be x1 of those guys. Okay, so, and this is going to be for j and x1. So I'm going to have a block that's a small discrete Fourier transform of these function samples on this little equally spaced grid of x1 points. And you can predict what all the other everything that's going to happen after that. So for whatever x2 is, I'll have the exact same thing happen there, etc. I'll have another little subsampled grid that I have to take a DFT over. And in total, I'm going to have the product of the number of primes that I use for both my Pn and my Qn, which is going to be this like k times log something to the n number of guys. So I'm going to have x k log something to the n by xk log something to the n DFT matrix that I need to multiply by an appropriate right? Equally spaced grid of that size. Okay, right. Whew. So, and this is ultimately just going to be equal to what I wanted, right? An encoded version of my coefficients. Yep, my Fourier coefficients times this sublinear time matrix construction that I wanted. Perfect. Okay, so, yep, and just a reminder, right? Every one of these xj's is going to be equal to some p times q that I choose in my construction. So p, lj, kj from definition of pn and qn. So I have control over what those are, determines everything about these k alpha coherent matrices, and also how you have to sample in that case. And all of these guys are going to be less than, if I choose these so that I have my best S term approximation guarantees in the theorem that I pointed out, all of these can be less than some absolute constant times S log cubed n. So these are all small FFTs that I need to compute of these different sort of relatively prime sizes. Okay. So the point is these, yep.
What is the star operator? Like the F.
Oh, this is just conjugate transpose. You can put inverse here if you want, because it's the same thing in the case. This is just a unitary matrix, so. Yep.
Sorry, Mark, can you remind how the log to the power c term?
This is going to be like log cubed. And it's going to be because our alpha was of size log n, and our k was of size s log squared n.
Okay.
And well, our alpha was of this size, and also the smallest value we need to make sense for the qn's is also of this size. So you sort of put them together when you get something sparse. Oh, yep. Well, that's where we get this. Yes. So let me see. So there are, yeah. I wanted this to be S. I'm switching between sort of substituting things for S and K. Let me just do it that way. But there are K Qs, and then there are roughly alpha. You can get away with alpha P's, and so you could write something like K times alpha would be an appropriate bound, or you can substitute alpha and K in terms of S, and then you get something that looks like this. But so the number of these guys, so we have all products all products are going to appear in these xj's of the q's that we use in qn, and I guess what I think I said they were, what notation did I use for those guys again? I'll tell you in a second. Yeah, capital K. Sure. So they're going to be K of the QLs, those primes, right? And for the P's, I just need enough that I have a bit testing matrix that works so that I can uniquely have enough columns for the number of n. I just need the product of the P's that I use to be bigger than n. So it's going to be something like log n P's. So I could write K log n, or I could substitute that K can be chosen to be something like S log n, and then write something like this. I'm being a little bit fast and loose, I guess, with how I choose K and sort of substitute it in. Does that make sense? Kind of.
Yeah, this is yeah.
Yeah. Good. Other other questions that anyone might have? Okay, so good. Okay. So if you believe that you have FFTs of this size, every one of these FFTs can be done in this log this time, because you have an FFT algorithm that you can run for each of these guys, and there are this number of them. So the point is, if you do it serially, it's going to be again s squared times log factors of n runtime to compute this, which you then put into your sublinear time recovery algorithm, which runs it again s squared times log factors time to give you an s term approximation to f hat. So putting all of that stuff together, you end up with a sparse Fourier transform, which you can see the details in, for example, improved approximation guarantees. Guarantees, which is a paper mine and Acha from 2013. And it goes through in gory details how you set all of this up and get all of these complexity bounds calculated and everything else. Okay. Very good. Little bit of time left, but not super amounts of time. So let's sort of pull back a little bit and think about the sets of samples that we need to have access to from our function in order to get this trick to work, right? In order to implicitly compute this sublinear time compressive sensing measurements of the Fourier coefficients and then run the stuff from yesterday. So we need these weird sort of equally spaced sets of samples from F associated to different numbers, right? Which is something that you might not have access to. In particular, if you have, if you want to do a discrete Fourier transform, you don't have access to these particular function samples of a function, right? You have exactly n equally spaced samples of the interpolating trigonometric polynomial, and that's what you have, and you have to deal with it, right? So, but you can fix that by using some unequally spaced FFT methods. You can take your equally spaced sets of samples in the discrete Fourier transform setting, use them to compute samples from F convolved with a really carefully chosen periodized Gaussian, whose Fourier transform decays really slowly, so it doesn't impact the Fourier transform of the interpolating trigonometric polynomial very much. And because it's a Gaussian, that is highly peaked in time, so you can compute convolutions with it on the time side really quickly, right? And then you can use those techniques to use equally spaced sampled points in order to approximate function samples at all of these values, and then run this algorithm. So I won't go into the gory details of how that proof works, I guess, but maybe after the break I can write down the discrete type of theorem you can get, because it'll be sort of important when we go to higher dimensions in a little bit. Okay, so I suppose I've just hit my hour mark, and I will let you go and wonder why you came back for a few minutes.
We have coffee too.
15 minutes maybe, I think.
Coffee can help.